work. And we will be, this is a long lesson today. So I anticipate we will be going till the end of class. Hopefully we get through everything. If we don't, there's always Friday. So pay careful attention. There's a lot of chemistry here. Today we're going to start looking at transition metals. One of those topics that I've said so many times. Yeah, we're going to ignore them for now. Yeah, we're going to ignore them for now. Yeah, they're more complicated. So now we're going to take a look at some of the reasons why transition metals are more complicated than the chemistry of the S block metals, those good old group 1 and 2 metals that we usually work with. So learning objectives, there is a whole lot of them. Yes.
Does that mean all of them are easy?
What?
Does that mean all of them are easy?
They are pretty, like, look at the command word, define, understand, explain, define, understand. Like, most of it is reasoning in terms of there's really no math in today's lesson. And a lot of this is just explanations, understanding what's going on. So the first one says define. Define means they want a word for word definition. So define what a transition element is. It is specifically a d block element that forms one or more stable ions with incomplete d orbital. We'll talk more about that when we get to that slide. But when they say define as, literally whatever they write afterwards in the standard, that's what they want you to rehearse. That's a rehearsed answer on a Cambridge exam. Just give the word for word. If you don't give word for word and you just give your best understanding, sometimes they'll give you the mark, sometimes they won't. So if you want to ensure that you earn the mark, you just write the word for word definition when it says define. We know because we got some of the tests back. I have to talk to Kaufman to see about like everybody else's, but we got some of the tests back when we were reviewing them. Like if you weren't word for word, they're very stingy with those marks if it's a definition question. All right, so 28.1.3, understand that transition elements have the following properties. They have a variable oxidation state. That means that transition metals, for example, iron +2 or +3. Didn't we already know that? A lot of this we're already going to know. That's why I'm breezing through it. So variable oxidation state means, for example, Fe could be +2 or +3. Copper could be +1 or +2. You do not have to memorize all the variations still, just like pre-ACE and AS. You don't have to memorize all the variations by heart, but you do have to know that they do have multiple possibilities for what their charges can be, and that's why we have to use a Roman numeral to say their oxidation number. That they behave as catalysts. We just went over that transition metals behave as catalysts. We rehearsed that rhodium, palladium, and platinum were the specific ones that were on the surface of the catalytic converter. There'll be a couple others that show up in today's lesson real quick, but they're all review. So this is something we already learned as well. They form complexes. That's what we're about to go over. That's today's topic. And they form colored compounds. I think I told you several times that one of the key components of transition metals versus group 1 and 2 metals is that transition metals often have color, whereas group 1 and 2 compounds, they don't. They're always white. So they form colored compounds based on their oxidation state. That'll be went over a little bit in today's lesson, but a lot when we come back from break. There's a lot more to say about it. So today, again, is mainly introduction to concept. Explain why transition elements have variable oxidation states. And it's in terms of their similarity and energy of their 3D and 4S subshells. So we'll be talking about that today, that the 3D and the 4S sublevels are super, super close to each other. And so that's why you could take more than one electron away. You could take the valence electrons away, and then you can also take away from the 3D, which is why, unlike groups 1 and 2 and 13 through 18, they have different amounts of electrons you could take away that would make it stable, instead of just having to simply fit the octet row. Explain why transition elements behave as catalysts. That's actually something that we kind of already did, but this idea that they have vacant d orbitals that are accessible and form dative bonds with ligands, we're going to go over that today. That's in the lesson today. That's the key part. Explain why transition elements form complex ions in terms of vacant d orbitals. Again, that sounds like a repeat to me. So understanding this idea of vacant d orbitals, we'll talk about today. 28.2.2. Define the term ligand. That's a fun word. So define the term ligand and then exactly what a ligand is, which is a species that has a lone pair of electrons that forms a dative bond to a central metal atom or ion. And so we'll be looking at types of ligands today. Monodentate, bidentate, and polydentate. To me, that sounds like dentist talk for some reason. I don't know. Like it sounds like dentures, but it's not. But we're talking about different types of ligands today. What they are. So monodentate, bidentate, and polydentate. And they want you to know these specific examples. Monodentate includes water and H3, Cl minus, Cl minus. Bidentate is N and ox, which we'll go over today. And then polydentate, where they want you to use the example EDTA, which is like ethyl diamine, blah, 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 blah. I'll show you the molecule when we get there. It's big. And it's in your homework. I made sure to include a question with it in your homework. 28.2.4, define the term complex. So notice all these definitions, understand definitions, tons of definitions in today's lesson. I apologize for Shahadat. He's gonna have a lot of catching up to do. Define the term complex as a molecule or ion formed by a central metal ion surrounded by one or more ligands. So that little diagram they showed you with the M2 plus in the middle and the 6 waters around, that's complex. And we'll be looking at a bunch of complexes today. And then finally, should we get the time, which I hope we do, but if we don't, it'll push into Friday. Describe the geometry, the shape, and the bond angle of different complexes, which are linear. They're going to ask you to specifically know the linear shape, square planar, tetrahedral, and octahedral, limited to those 4. So you won't see any others, just linear, square planar, tetrahedral, and octahedral. And when they say describe, you're also going to have to draw. So you'll have to draw the correct shapes. State what is meant by coordination numbers. Predict the formula and charge of complex given the central metal ion, the charge of its oxidation state, the ligand, and its coordination number or geometry. So that's like a lot of words. That's just like a lot of big words. So we're going to break this down piece by piece, starting with what are transition metals, and then we're going to get more into complexes. But today's like a lot of establishing information. A lot of content today, but a lot of important content. We're going to go through electron configurations quick. Even though like that's here, it's something that I gave you practice questions on Monday, and that I will be putting those practice questions along with the other way ground in the grade book. So please make sure that if you didn't do that already, that you go do that, because I will be updating the grade book shortly for that. There was an assignment on electron configurations. Yeah. It should have taken not that long to do. It was a gift assignment. And then you had an extra credit packet for winter packet that you didn't have to complete on Monday, but I gave it to you if you wanted to get started on it. And that's optional, but it is worth 2 grades, extra credit assignment grades in the grade book. I looked and it does make a pretty good impact in your grades, like 5 or 6%. So if you are within that amount to your next grade, do that extra credit packet, plus it helps you to study for the quarterly, which is coming up when we come back from break. Not right when we come back from break, like a week after we come back from break. The second week we come back from break, the first class period will be your quarterly. That was what was voted on, by the way, to have it like January 12th. So that's when you're gonna have it. All right, so electronics, we're gonna go through pretty quick. The main way that I would memorize doing them is with the periodic table, like knowing your S, your P, your D, your F, and then knowing for the D block to subtract 1 from the S. S continues to be ignored. There's nothing in here about intertransition metals. Chapter 24, which is the chapter that we're going over today, starting to, has nothing to do. We're not even gonna touch the F block. If you want to do F block chemistry, major in either inorganic science or major in nuclear science, because in nuclear science you work with those F block metals like uranium, plutonium. Other than that, we really don't do much with the or physics. Yes.
On the quizzes, one of the questions had
An F?
no. Well, yeah, that was with gold, but it had the same where it's like copper, where it had the same.
Yes.
Where like it has not, it only has 1 in the S block, but
I think something else interesting shows up with copper, silver, and gold in today's lesson, that they all have some other similar property due to them all having a very, like, they're in the same group, so they have the same properties, generally speaking. What?
No, I'm saying they're all expensive.
Well, and they all conduct electricity spectacularly. All right, so you good?
And they don't react, you know.
They're not very reactive. But there is something else actually also in this lesson about them that showed up that I was looking at last night that I saw in the textbook that I was like, oh, they shouted that out. That's interesting. That I'll bring up today. All right, so these are some like review questions. In electron configurations, electrons fill 3D orbitals. We know they're higher than the 3p and 4s orbitals. How many 3D orbitals are there? 5. And how would we write them? This is going to come into play later in today's lesson. We would write them as little boxes. I know you're so excited to hear this information I'm about to tell you. This is the unit where you will have to memorize the shape of the d orbitals eventually.
What do you mean the shape? What are they shaped like?
It's the dumbbell with the circle.
Like this is one of them.
Yeah, both dumbbells.
The double with the donut. The double dumbbell. That's coming. It's not in today's lesson, but it's coming to memorize because we're going to be looking at the D block a lot. And the idea that these d orbitals will actually be split into 2 different energies by ligands. That's going to be happening later on in the unit. But for now, we know that there are 5 orbitals whenever we enter the D section, correct? And that electron should fill 1 into each orbital before we put a second into any orbital. How many electrons would we put in each orbital in total? 2. So how many electrons in total could be held in the 3D sublevel? 10. And so the next thing I wanted to bring up, and let's see if it shows up here. It'll show up very shortly, is what is a transition metal defined as then? Because it's actually not exactly how it's been presented at the foundational level. Like some elements that are in the D block are technically not considered transition metals. Zinc is one of them. So what is a transition metal? Its official definition. I put it in a box so that you have to memorize this. This is one of the ones that shows up in the standard that they want the word for word. Transition element is defined as a D block element that has 1 or more stable ions that have an incomplete D subshell. What do we mean by incomplete D subshell? That means that it would end somewhere between D1 and D9. Incomplete means not complete. 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 10. Because 10 would be complete.
Copper has complete D subshell.
Maybe. Sometimes.
Okay.
Forms 1 or more stable ions with an incomplete D sublevel. So some D block elements are not considered to be transition metals for this reason. If they end up having no electrons in their 3D subshell, or all electrons filled. So the examples that we have are scandium 3+ and zinc 2+. What is the electron configuration for scandium 3+? And it's going to show up here on the question 1B. What's the electron configuration for scandium 3+? Scandium 3+. It would be what? Just argon. So it would be argon 4s0, 3d0, which you do not have to write, right? You just write it as argon. But the key here is that there are no d electrons. And you cannot have a transition metal if there are no d electrons, because some of the key properties of transition metals have to do with the fact that they have d electrons that can jump between the split energies of the different d orbitals that's coming later on in the lesson, like later on in the units. So this doesn't have any d electrons, so therefore it's not considered to be transition. The other one is zinc that you have to know. Zinc has a 2+ charge only. It's actually one of the ones you were supposed to memorize, right? What were the others? So if zinc, shouldn't cadmium also be not considered transition? So why do they only shout out zinc?
It's common.
Because when we are studying for Cambridge, they always say pretty much we're limiting your main study to 3D. So we're just studying the elements scandium through zinc, but you should still know that elements in the same group have similar properties. So anything that applies to zinc should usually apply to anything that falls below it as well. So technically the same would be true of cadmium. Cadmium would not be a transition metal because it also has that fixed 2+ charge. Yes.
What about zinc?
Yeah, we'll get there. So zinc 2+, so that's gonna be argon 4s0 3d10. And that's its only option, right? 4s0 3d10. Interesting note though, you said, somebody mentioned, Luke, what it was, mentioned copper. Copper can be +1 or +2. These are the two options for copper. So if we had copper +1, what would its electron configuration be?
And no one.
It would be argon 4s0 3d10. But what would copper +2 be? 4s0 what? 3d9. Do you agree? What's regular copper? That's not charged. It's an exception, isn't it? So it's argon 4s1 3d10. So when you take the first electron away, you take it away from 4s. When you take the second electron away, you take it away from 3d. What you're going to notice in all the practice questions that you see is that every time we're using copper as a central metal ion that I've ever seen, we're using copper +2. And even copper sulfate, copper fluoride, it's always copper +2. Because that has, this is incomplete.
Do you have copper with a higher charge?
I've not seen it. It's not listed as a common one. I've not seen it in practice with a higher charge. All right, so far so good. So you've got to know scandium and zinc are not considered to be transition metals because they do not have incomplete D sublevel. For scandium, its D sublevel is empty. For zinc, its D sublevel is full. So, and those are the only ions for these two that you could have, which is why they're considered not to be transition metals. Whereas with copper, copper had that +1 and +2 option. So although copper +1 would be full, copper +2 isn't. So copper +2 is still, that's why copper is still considered a transition metal. Silver is a very interesting one. But technically, we're not fully studying the chemistry of the 4D, even though silver will show up here and there. You'll see it discussed. Silver, however, also has a lot of colorless compounds, like silver nitrate is white. All right, so things to remember about electron configurations. You need to know chromium and copper are exceptions in this class, and that both of them will take one electron from the 4s orbital to give to the 3d. So they always end 4s1. So like chromium, if you'll recall, is 4s1, 3d5. And copper was, we just saw it, 4s1, 3d10. That's something you've got to be aware of. And if we are taking electrons away from transition metals, we always take them away from 4s first, and then we take them away from 3d afterwards. Something to be aware of before we move forward. Why do we take from 4s first? Is the farthest. And I wanted to show you, this is actually coming from my previous lesson. Something that I would have shown you if you were in my class over 2 years ago. This is the Aufbau principle, like just the general standard Aufbau principle, which is when electrons are filled, they're filled in orbitals of lower energy before they're filled in orbitals of higher energy. And so if you look at 4s and 3d, their energies are almost the same. They're not exactly the same, but they're almost the same. So because of this, it's very easy to take electrons away from either the 4s or the 3d, which is the reason why transition metals can lose both their 4s electrons and their 3d electrons and still be considered to be stable. And so I just wanted to bring that up. And this concept here is going to come into play several times in this lesson. So I just wanted to bring that back up, that 4s and 3d have very similar energies to each other. And in Cambridge's standards, they wanted you to demonstrate that you understood that. So quick question. We're going to go super quick through this. Titanium, what is its electron configuration? Let's do the noble gas version. So it would be argon and then what? 4s2, 3d6. Chromium, that's an exception, right? So what is it?
4s2, 3 and 4.
That's what you think, but it's not. 4s2, 3d4, but it's an exception. What happens in the exception? Yes. You give one electron from the s to the d. So this should be actually 4s1, 3d5, like that. Why what? For this is an exception. Chromium and copper are exceptions you've got to know. So iron 3+. What's regular iron?
Argon, 4s2, 3d6.
So iron 3+ would be argon. Take away the 2 from the 4s first because it's the farthest away. It's the valence shell. And then how many do we take away from D? 1. So it's just 3d5. And you can write the 4s0, but you don't have to. And for nickel, regular nickel is argon 4s2, 3d8. What's nickel 2+? Argon 3d8. Are these all considered to be transition metals? Titanium, chromium, iron, and nickel? Yes, because they all have something that ends between D1 and D9 in their electron configurations, whether it's their regular or their ion. Could we also use this to predict their maximum oxidation number? Could I, for example, predict how many electrons I can possibly take away from titanium? What do you think it is? How many electrons do you think you could possibly take away from titanium? 4. Because you can take away the 2 from the S and the 2 from the D. How many electrons do you think I could possibly take away from chromium? 6. And we've seen its oxidation number B6 in a very common polyatomic ion that you work with a lot called dichromate. Cr2O7. Dichromate has that little 6 afterwards because it has the oxidation number of 6 plus 6. And that's the maximum it can have because you can take the 1 electron away from the S and then the 5 away from the D, and that gets it to its nearest noble gas. So that's the maximum stable oxidation number. Okay, so I know you're so excited to see this. There's good news here. The good news is that you do not have to memorize all of the possible variations of positive charges you're going to see for transition metals. So I'm going to just right here, do not memorize this chart unless you want to. Like if, for example, in the science bowl, they randomly asked you what was not a possible oxidation number for a specific transition metal. I mean, I guess you could memorize a pattern here. There's a bit of a pattern, but you don't have to. So you do not have to memorize this chart. But what this chart gives you is the different metals, transition metals, and their colors when they have the different oxidation numbers. So for example, titanium is colored when it's +3. When it's a compound where it has a +3 charge, it'll have a purple color. Chromium, I think I've shown you dichromate before. It's orange. And that's when it has the +6 charge. But when chromium is +3, it's green. And when it's +2, it's blue. Copper +2 is blue. That's its color in water. Some of you might say, but I've seen copper compounds that are green. That's coming later this unit. Why the colors can end up being different. So these are their regular colors, like if they were in water. For example, this would be the colors that they would possess, or regular compounds as they exist. Iron +2 +3. We've seen iron +2 in iron sulfate when we've done that titration with permanganate. Yes. Okay.
Everyone has.
All right, so don't memorize the chart, but be aware that transition metals have colors, different colors with different oxidation numbers. That's at this point all I need you to know. Notice zinc doesn't have a color. Notice here copper, they do list it with a +3, and it doesn't have a color there. All right, so things you got to know about transition states that Cambridge expects you to know. They expect you to know that transition metals have similar physical properties to each other, that they have variable oxidation states, that they form colored compounds, that they operate as great catalysts, and that they result in complex formations. This is literally a lot of stuff that we went over before, just stated in a standard. You've got to know these are properties about transition metals. Catalysts, specifically. What are some transition metals we've seen as catalysts? Iron in the Haber process. What's the Haber process? N2 plus 3H2 is one that was studied a lot in equilibrium and AS chemistry. Goes to 2NH3. It was the exact example that was used in class for how a heterogeneous catalyst works in the textbook. The metal for that is iron, and you are supposed to know that. The contact process is the process for making sulfur trioxide from sulfur dioxide. So that's SO3. And the catalyst for that one is V2O5. Also a solid, also a heterogeneous catalyst. And then one that I wanted to shout out, that's an old school at this point reaction. You haven't seen it in forever, but it will come back shortly. Organic is on its way. But after this unit, we start organic. So nickel in the hydrogenation of alkenes, meaning when we took this, remember when we had an alkene and then we added H2 to it and we turned that alkene to an alkane. We needed high temperature and we needed a nickel catalyst, nickel or platinum catalyst. Right? Transition metals. So Cambridge wants you to be aware that transition metals are often used as catalysts in many different chemical reactions. These are a few of the ones that I would just know by heart because they're shouted out a lot. All right, so I'll pause. We're good? Move on? Okay, so why is the maximum oxidation state of manganese +7? Isa. Right. So literally you can just go here and count backwards. 1, 2, 3, 4, 5, 6, 7. Maximum oxidation state. Ah! Let's see. Yes. Thank you. Secret Santa. They gave me some Pokemon cards. Very exciting. You said gotta get them all.
Packs or was it a card?
It's a card, like it's a pack of cards.
Oh, miss, that should be the end of the class.
The end of class. Okay. 9:20. 9:20. All right, let's continue. Zirconium is in the second row. They need titanium. What do you think is maximum stable oxidation state is? And why? Zirconium. What do you think? Maximum stable oxidation state of zirconium. +4. It's +4 because that's how many accessible S and D electrons we have going to zirconium. 1, 2, 3, 4. 5s, 4d. Periodic table predicts it all. So you can write out this electron configuration. It would be krypton, 5s2, 42, and then these are the 4 electrons that could be taken away. Yeah.
Including that same pestilence.
That could be taken away? Sure, but that in practicality are taken away? No.
Yeah.
Because zinc is a fixed charge one. It has +2. Zinc, cadmium, and silver have fixed charges. Give the formula of the oxide of zirconium, assuming it has that oxidation state. So if zirconium has +4, what would its formula with the oxygen be? Oxide means you're putting oxygen with it. So what would its formula be with oxygen? What's the charge of oxygen? So how would we get the formula? So just ZrO2. Back to Prius. Actually, Prius has a test on this today. You would crisscross. You would get Zr2O4, and then you would simplify, which means divide both by 2. And that gets you here. Hopefully we remember how to do that. All right, on the next slide, just are a couple of common compounds that we've seen before where we have higher oxidation states in our transition metals: chromate 6 and manganate 7. That wonderful purple solution we will be working with not too long from now. Our titration this unit will be a permanganate titration.
6 and 7.
Yeah, it is. Like part. All right, so ligands, here we are. So the first part of the unit was basically just describing what a transition metal is, what defines it, like what its general properties are. So now we are to the main show, basically, of this lesson, which is what is a metal complex and what is a ligand. And so if I have a metal, transition metal ion, it has what we call vacant d orbitals, meaning it has a lot of space, some have more than others, to accept electrons. And so what happens is a ligand will come in, like water, and it will donate a pair of electrons to that metal. So a ligand is a species that attaches to a metal through a dative bond. So it donates a pair of electrons. So it donates a pair of electrons. They call it a coordinate covalent bond, but Cambridge usually calls it dative. So you can cross that out and use, it's not wrong. Coordinate is right if you wrote that out, but they usually use the word dative bonding to describe this process. So it's a dative covalent bond. Dative is an easier word, less letters anyway. The ligand must have a pair of electrons it can donate, or else it can't be a ligand. So there are certain things that can be ligands and certain things that cannot. These are possible ligands that you will encounter over the next few slides. Water, one of them. NH3, another one. Does that have a pair of electrons? It's on the nitrogen. OH minus, CN minus, Cl minus, Br minus, and I minus. Yes.
This one was also base. Yeah.
That is a great question. So technically, there are 3 acid-base theories. Cambridge only discusses 2, the Arrhenius and the Bronsted-Lowry. But technically, this is a Lewis acid and a Lewis base. And I believe it was even mentioned in the video he showed. There's a 3rd acid-base theory. I can get into that with you later because it's not part of the Cambridge curriculum, but technically, yes, this is an acid-base theory. The metal is operating as a Lewis acid, and the water is operating as a Lewis base. So this is the idea of what happens. And so what happens is these ligands will go and coordinate to the metal in the middle. So every one of these arrows represents a dative bond, which is a pair of electrons donated to the metal. I want to say metal in the middle. Metal in the middle. The metal in the middle. The metal that's in the middle. It's going to be a central metal. Central metal atom or ion. That's what we're talking about here. And so ligands are the species that are on the outside of the metal that are donating electrons to it. And the requirement for a ligand is that it has to have at least one pair of electrons. So what would not be a ligand?
Neon.
Not a ligand. Well, neon don't do anything. But for example, NH4 plus is not a ligand. Why isn't that a ligand? There ain't no pair of electrons to donate. So not a ligand. No donation can happen there. For an electron pair donation, whatever you have has to have an electron pair. So being able to draw a Lewis structure here would be helpful to know whether there's a pair of electrons or not that could be donated. All right, so we're going to go ahead and continue into definitions. So the first definition was a ligand. A ligand is a species that can donate a pair of electrons, and it should be donate electrons, but it's going to be pairs of electrons. So you should insert the word pairs there because it is a pair of electrons that's being donated, not just a single electron that's being donated. And then we'll continue the next definition. The next definition is a complex. So what is a complex? This is when I put the metal and its ligands together. We call this a complex. So instead of writing it like this, we write this as the chemical formula. So this is the chemical formula for a complex. This is saying this cobalt has 6 NH3s that are donating to it. So it would look like this if I were to write it out. NH3, and I don't want to write out the whole thing, but this is going to be it. NH3, NH3, NH3. You see me showing geometry? Uh-oh. NH3 and NH3. Later on in this lesson, we're going to go more over geometry, but the idea is that each of these NH3s are donating a pair of electrons to the cobalt in the middle. The cobalt has a positive 3 charge, so the overall complex will also have a positive 3 charge. And so this is how we would write it out in a chemical formula. You're going to have parentheses around your ligand, and you're going to have brackets around your complex. So yes, remember in math, it's kind of that thing where the first parentheses is a parentheses and the second parentheses is a brackets. This is what's going on here. There'll be parentheses and parentheses. All right, so why do these form? Part of it is that when you form your complex formation, it spreads out the ionic charge around a larger area, which stabilizes the metal ion. And here's where the good stuff is. The next slide. Yes. The next slide talks about how does this happen. And so looking at copper, what happens is the following. Copper has access to all of these orbitals. The whole entire 4th energy level is empty. And so what happens is in this complex, which is CuCl4, every chlorine donates a pair of electrons to fill an orbital. And so then you get what's called, oh, you're just going to be so excited for this, sp3 hybridization. Because one s orbital merges with 3p orbitals. And you get sp3 hybridization, and these 4 chlorines fit those spots to make them 4 bonds. And that's how you get CuCl4. Has a 2 minus charge. Why? Why does the complex have a 2 minus charge, even though copper has 2 plus?
Because
Each chlorine is
2.
minus 1. So the whole overall thing would have a -2 charge as a result. When they wrote this, because I picked this up online somewhere, they didn't write all of chlorine's electrons, just the ones that we're donating. So chlorine does have its full octet. If you are a completionist and need to see that, it does have its full octet.
is there able to be like PD hybridization?
Yes. And then we'll go over what Cambridge assesses and doesn't assess, but I did include everything here. Cambridge stops like the hybridization concept at sp3. However, technically, if you have an octahedral complex, you have a sp3d2 hybridization. All right, so this is how a complex forms at the electron configuration level. Due to, here's another example, Fe2 plus has vacant d orbitals. It has the ability to receive electrons from water molecules. So how does that happen? Let's go ahead and write out Fe2 plus's electron configuration. So Fe2 plus, it would be argon. And we're going to use the boxes. So it would be 4s0. Do you agree? And actually, it would make more sense to write the 3D first here, just because of what I'm about to show you. So it would be 3D. How many electrons are in the 3D? Yes. So 1, 2, 3, 4, 5, 6. And then you've got 4s, and what else do you have access to? 4p. And what else do you have access to? 4d, right? 1, 2, 3, 4, 5. So what happens here? They're telling you that you're getting 6 waters going around iron. So what's happening? You have 1, 2, 3, 4, 5, 6 of these orbitals that are receiving pairs of electrons. So these would all merge. So you're absolutely correct. You would get sp3d2 would all get pairs of electrons from the waters. 1, 2, 3, 4, 5, 6. Octahedral would be its geometry. Could they ask you to draw this geometry? Yes, it's coming. Yes.
What happens when the 5s or something?
What do you mean 5s?
Because before 40, shouldn't the 5s or become 2?
That's great. A great question. It doesn't though. Not in this scenario.
Okay.
I actually also posted an article on the Google Classroom with the textbook chapter because I figured the textbook doesn't do enough explanation of what's going on here. So I put an article up as well that explains it even more. So it's the CK12 one. There's one that I found on CK12 that I posted that goes more over this process. Next question, does Cambridge actually need you to show this? The answer is no. This is just for you to kind of build an understanding of how this even can happen. That these metals can receive more than 8 electrons because they have the space to fill more than 8 electrons. This has a fancy name. It's called the 18 electron rule. If you were to study advanced inorganic chemistry, meaning that transition metals have an expanded octet. I'm gonna write that down. So although this isn't like in the Cambridge Standard, this is just like general chemistry knowledge information. Transition metals can hold a max of 18 electrons. We call this the expanded octet rule,
The octet means 8.
which is why it's called the 18 electron rule. So instead of being called an octet, it's called the 18 electron rule. And if you want to look into that more, just for your own benefit, there's a lot of references, material out there. I didn't learn this until my 4th year in undergraduate chemistry, like this topic. So a lot of what's in this unit is stuff I have to be careful not to go too far into detail and just kind of try to limit it to what Cambridge is asking for you to know. But if you want to look into this more, you can. Like, how does this happen?
It's important.
What?
It's important.
Interesting. It should be interesting because there's a lot of interesting chemistry that you can do with transition metals, especially if you're looking into the generation of catalysts and like solar panels. Like, there's a lot of interesting chemistry that different transition metals can do. All right, so the next definition is called the coordination number. And the coordination number is just how many coordinate covalent bonds are attached to the central metal ion. So this is something that you simply need to count. For example, here, how many data bonds do you see from the waters to the iron? How many arrows? You see 6, right? So that means the coordination number is 6. The coordination number is just simply how many bonds, data bonds, are going to the central metal ion. We call that the coordination number. And there are specific ones you're going to be needing to know for this class. Linear, coordination number of 2. Trigonal planar, you are not going to see. Cross that one out. Tetrahedral, coordination number of 4. Square planar also has a coordination number of 4. You will not need to know the hybridization for D. You will not need to know the hybridization for D, but you do need to still know hybridization for 2, 3, and 4 groups, which is SP, SP2, and SP3, just in general. But the D's is not part of the Cambridge curriculum for some reason. And then these you do not need to know for this chapter, or this chapter. They won't show up because there's nothing with a coordination number of 5. And there is plenty with a coordination number of 6, which we call octahedral. And so these shapes you're going to be responsible for knowing are linear, tetrahedral, square planar, and octahedral. Those are the 4 shapes that you're going to be responsible for knowing and being able to draw. And so we'll be going over that shortly. The coordination number is just how many bonds are going to the central metal atom. It could be 2, 4, or 6. Yes.
Can we say they give the theta instead of coordinates?
Yeah, I wrote theta here.
Okay.
Notice I'm using both because you can use either. So the next is types of ligands. You are responsible for knowing types of ligands and the definition for all of them. They're called monodentate, bidentate, or polydentate. And so a monodentate ligand, by definition, donates only 1 pair of electrons to the metal in the middle, the central metal ion. The key characteristic about a monodentate ligand is they're small. So these tend to be small molecules and ions are monodentate ligands. There are only 2 bidentate ligands you're supposed to know by heart, which I'll show you on the next slide. Bidentate ligands donate 2 pairs of electrons to the same metal. They have to be large enough that they can bend around. That's what's being shown to you here. They have to be large enough that they can bend around in order to donate from 2 different directions to give the proper bond angles. You'll see the example shortly. And then polydentate is a ligand that donates more than 2 pairs. The only one you are responsible for memorizing is EDTA, EDTA, which donates, I believe, 6 pairs of electrons. So a polydentate ligand donates more than 2 pairs of electrons to the same metal. There's a very interesting polydentate ligand that exists. See if I can pull it up. In biology. So I'm going to go ahead and pull it up. Have any of you ever heard of hemoglobin?
I knew you were going to say that. How about-
Because of the iron.
Yes. Fe2 plus in the middle.
Okay, it's just
Oxidizing.
massive. Yeah, it's massive.
Hemoglobin structure.
Do you know what else is massive?
Hemoglobin. Here it is. Good old hemoglobin. Where's the Is that the right word? Ah, there's the molecular structure. I'm just looking for this. So this is iron 2 plus, and this appears to be extremely square planar because it's got the X that's a square planar, like it's shaped like a square. And what they're not showing you is these are all arrows. Like these are all dative bonds from the nitrogen to the iron in the middle. This is hemoglobin, a example of a classic molecule called a porphyrin, which is a very, very, very important class of ligands. And this is biochemistry. So ligands would show up in biochemistry and biology if you decide to take an advanced biology class. The one that I said that Cambridge wants you to know, there's another one. It's called EDTA. Let's take a look at EDTA. EDTA. Structure. And no, you don't have to memorize the structure by heart. They would draw it out for you. Just like hemoglobin, you do not have to memorize that by heart, but they will draw this out for you. And you'll have a homework question on it from a paper 4 so you can see. This is EDTA. And the type of question that they would ask you about EDTA is, where are the 6 donations coming from? Yes. Yes, you can see I'm showing up. It's kind of hard. This is a small image, but where you have pairs of electrons in different areas, that's where the electron donations would be coming from. So you could have one there, one of that nitrogen, one of that nitrogen, and then 2 over here from different areas. So very large molecule can do a lot of electron donations. And so that you have to be aware of. Okay, so those are your types of ligands. What are the 2 bidentate ligands? These they want you to memorize. They're going to shout them out either by name or by their 2-letter abbreviation. And you've got to be aware of them. The first one's called ethane thioate, where we go ahead and show the pairs of electrons. You would have something being donated there and something being donated there. Go ahead. This is why it's bidentate. The oxygens are donating from 2 different directions. So this is called, the official name is ethane thioate. Its abbreviation is OX. Does anybody know why?
Oxford.
Bad answer. It actually is also a polyatomic ion. This polyatomic ion, I don't ask you to memorize because it never shows up until this point. The name of this specific polyatomic ion is oxalate. That's its common name. That's where it comes from. C2O42 minus is oxalate. And so that's why they call it ox, which, whatever. That's why it has that. So ox means it's oxalate, C2O42 minus, but these are the pairs of electrons that are being donated. And it's common name is oxalate, which means oxalic acid, if you've heard of that, is actually acidic form, H2C2O4 is oxalic acid, which I'm sure I have plenty of that. I've used it for Cambridge Labs before, yes.
But the other oxygens also donate in theory? I mean, they have.
It's direction. So the direction they would be coming from these. But I guess in theory it could be. But I'm sure it's from these. And then for this one, it's very clear where the donations are coming from. For the for 1,2-diaminoethane, which is ethane with 2 amine groups on it, basically, they call that N.
Or English.
I don't know why they call it. I think. No, I don't know what they call it yet. I got the ox.
Ethane and then the amino. The E from the ethane.
It's because it's in English.
And I don't know, but that's there too, so it's very confusing. But anyways, En is 1,2-diaminoethane. En is the one with nitrogen is the one I would remember. Like N has nitrogen. Ethane with nitrogen. The end. And so the 2 donations are here. These are the 2 donations that are going to the central metal ion are coming from the 2 nitrogen groups. So notice that to be bidentate, you have to have a larger molecule. It has to have at least 2 central atoms. Notice that both have at least 2 central atoms. Whereas your monodentate ligands, that won't be true. Monodentate ligands have just one central atom typically. They're small molecules. They're just a couple of atoms. Here they're larger. And did Cambridge say you have to know these two by heart? They want you to know these by heart. And how could this show up if it didn't show up in its full displayed form? How could they have written this otherwise? What would its structural formula be? H2N, CH2, CH2, NH2. This would be its structural formula.
Do they ever have us like draw 1,2 diaminoethane?
That would not be the standard. No. But they expect you to recognize it. And they'd expect you to, you'll see when you get to lesson 5, how they expect you to draw a little bit more. Because you are going to have to do 3-dimensional drawing. All right, so this next slide, oh boy. I don't even know what slide are we on out of the, do you know what number are we on? We're on 23, okay. I said anything we don't get to today, we're doing next class. The next slide, oh boy. So these are different types of ligands. I got this from the current textbook because I wanted to make this as clear as possible for you on what the expectations are. These are the different types of ligands that you have and their most common coordination number. So right here, most common coordination number, because there's all kinds of exceptions in this unit that may have a few tiers from the exceptions, but this is their most common coordination number. Water usually forms a coordination number of 6. And so next time you're doing a lab, when we do the lab for this topic, if you look at the bottles of the chemicals that we have, a lot of times it'll show if it's a hydrate, like how many waters are actually attached. And so you may have seen that when we have copper sulfate, it's been written on Cambridge papers that they'll write it as CuH2O6 because 6 waters combined with copper in water. That's actually copper AQ. So how we've been doing copper 2 plus AQ, it's actually been copper 6 waters 2 plus. That's copper in water. And so ammonia also coordinates usually as a coordination number of 6. And the shape of any complex that has 6 is octahedral. Do you remember that from AS Chem? You're going to need to. It's coming back. If I have chlorine, chlorine usually does 4, not 6. And yes, Cambridge expects you to know that it's 4, and they expect you to know that it's typically tetrahedral. So if you see chlorine as a ligand, it's going to be tetrahedral, and it's going to have a coordination number 4, which means you need 4 of them. Cyanide is also 4, but it goes square planar instead of tetrahedral. And that's what's being shown here. I'm going to explain this in a little bit. Hydroxide, 6 when it forms a ligand, but sometimes it doesn't form a ligand. Sometimes it just precipitates hydroxide. Like copper hydroxide will just become CuOH2. That's for another lesson, another day. But when it does coordinate, it coordinates as 6 along with SCN minus, which is thiocyanate, which is the first time I think that's officially showing up in the topics. Another polyatomic ion has just entered the room. Thiocyanate, whenever you see the thio prefix, thio means sulfur. They use it a lot in biology because there's a lot of sulfur compounds, disulfide bonds in biology. So that's that. And then this is your ethane dioate and your 1,2-diaminoethane. So those have coordination number 6. So most are 6, notice. Most are 6. Lots of 6s and 2 4s. The 4s are the chlorine and the cyanide. And then I wanted to show you this because I was trying to figure out like how deep they want you to go. Because in order to understand if something's going to go tetrahedral or square planar or octahedral, you actually need to have an understanding of orbital splitting and crystal field theory, which is very advanced chemistry. So you do not need to know that, but if you ever, you want some fun winter reading, go look over crystal field theory. And it talks about how ligands split everything and how you get the possible, there's like high energy versus low energy variance, high spin versus low spin, all kinds of fun, very advanced chemistry in there that they do not put in the standards here. So this is a very limited topic. We're limiting it. But I want to show you what the textbook says here. They have the complex ion formed between a transition metal and a larger ligand says it can only fit 4, not 6 ligands around the central ion. And so they're telling you that it would be square planar if it's CN and tetrahedral if it's CF. And my brain was trying to wrap my head around like how chlorine is larger than NH. I guess it kind of is. Do you think chlorine is larger than NH3? Why would chlorine be larger than NH3?
Has 3 levels.
3 levels versus nitrogen has 2 levels. So they're saying that chlorine is a larger atom. So therefore, it's not going to fit 6 around it. It's only going to fit 4.
So chlorine plus negative charge, so.
It makes it even larger. The anion makes it even larger. So it's a little bit larger than I guess if you're comparing it to water, which is small. And NH3 is small. And then CN also has a minus charge, which might be like increasing its size as well. And that's why these two go tetrahedral and square planar. And so they want you to know that. And then this is the spot in the textbook that I added this last night because I was reading through. I was like, how are we supposed to know this happens? And the explanation is you're just supposed to know this. For silver, for copper, and for gold, they are the only 3 that you're expected to know form linear complexes with ligands. So they're the ones that have a coordination number of 2. Coordination number equal 2. So a few transition metals. Hey, copper, silver, and gold. Where are they? They're literally the same group in the periodic table. So they're the same group and they all have the same charge. This is Cu plus, silver plus, and gold plus 1. Same group, same charge. They all form linear complexes. And so you're expected to know that silver, gold, and copper, copper 1, silver, and gold all form linear complexes. All right, so now with this being said, let's try a couple of practice questions. We've been doing a lot of content. What are the types of questions you'd actually be asked here? This is from the textbook, so not quite to paper 4 yet. First one, here is a complex. Can you first give the oxidation number of the metal? What would it be?
Plus 6.
3.
Why plus 3?
H3 has 0 charge.
NH3 has no charge. You're expected to know the charge of all the ligands. So if it has no charge, if this is 6 zeros, then the charge on the outside is the charge of the metal. All right, what's the coordination number here? 6. And what's its predicted shape? 6 is always octahedral. All right, first try. Let's try this again. All right, next one, oxidation number for nickel.
Plus 4?
Plus 2. Why is it plus 2? CN is minus 1. The whole thing is minus 2, right? So the way that it works is if this is -1 and there's 4 of them, then this is -4. What number minus 4 is -2? Positive 2, right? 2 minus 4 is -2. So it's really that same idea from when we were first learning oxidation numbers. You could call this your x if you want, that's what you're solving for. So it really becomes x minus 4 equals -2. Bring the 4 over to the other side, and you get x equals plus 2. Does that make sense? Marinate. It's +2. Coordination number here. 4. And that is basically, like I said, unless you want to investigate crystal field theory and like high energy versus low energy splitting on your own time, which is way beyond the scope of this class, it's just memorize that CN is square planar and CL is tetrahedral. Yes. You can scan show up, yes. All right, this one, COEN3, oxidation number.
The 0 or in blue?
+3. Ethyl has no charge. This is H2N, CH2, CH2, NH2, no charge.
That's what Ian said.
Yes, that's what EN stands for because you have to memorize it. That EN stands for this, that it has no charge. Memorize these. Yep. So I said there's tons of content here. Coordination number. What's the coordination number?
Oh.
Why is it 6? Go ahead.
Ian has 2.
Because this is bidentate. Which means that each one of these actually has 2 dative bonds. Yes? So the total dative bonds is 2 times 3, which is 6. Which means its predicted shape is octahedron. Remember I told you that for coordination numbers, you're only going to see 2, 4, and 6. 2 for linear, 4 for square planar or tetrahedral, and 6 for octahedral. So if you answered 3, may not be right. You might have made a mistake for the coordination number. All right, so that's the first type of question from the textbook. And this is the first, like, besides electron configuration, actual question with this topic we've actually seen. Next question from the textbook. Can you identify if these ligands are monodentate, bidentate, or polydentate? Which, I didn't even put polydentate as an option there. Yes. Text 3. There's 3 of them. It's under you. Thank you. Because there's 3 of them. Each of them is giving 2. So 2 times 3, 6. All right. H2O. Monodentate, bidentate, or polydentate? Monodentate. NH3. Mono. Cl minus. Mono. SCN minus. Monodentate. Ethane dioate. 5. Dentate. And 1,2 diaminoethane. 5 dentates. All right, here's paper 4. First question, paper 4. In aqueous solution, iron can form complex ions which contain ligands. What is the type of bonding that occurs between a ligand and a transition element? Go ahead.
Dipole ion, dipole ion.
Dative.
Oh.
Dative.
Okay.
Between the ligand and the transition element is always a dative bond. This is saying like between the metal in the middle and the ligand, what is happening here? Dative bond, right? Name it. It's called dative. If you want to, you can say dative bond. Or coordinate. It would be like saying more letters. Coordinate covalence. Define monodentate. Ligand. What is it? And this is very common. Define monodentate or bidentate. What is that? Go ahead, Francesca. A species or substance. You gotta say, like, specify. Species or substance that donate 1 pair. The key word is 1 pair of electrons, keyword, to a central metal. And you can either say atom / ion. If you say central metal, that should be enough. But I'm gonna put atom / ion. Because it could be an atom doesn't have charge, ion does have a charge. All right, so that was worth 2 marks. 2 marks. And it's common. I would know these 2 marks. I would say species donates 1 pair of electrons. So where's the second mark? That it's donating to the central metal. That's the second mark. Like this is literally like say 8 words for 2 marks. That is a lot easier 2 marks than some of the other 2 mark questions that you will see. Coming soon. All right, the next type of question is also a common type of question that I've seen where they give you a chart and they partially fill in the chart and they ask you to fill in the rest of the blanks on the information that they're giving you. So they're providing you information and they ask you to fill out the rest. They're telling you that, hey, this metal is chromium, this ligand is CN. The charge on the overall complex is 3-. Can you figure out the coordination number? How could you do that? If I were to put chromium with CN, how would I know how many CNs I need? This overall is 3-. So what would we do? This is fixed. You have one of these. So what can you change the amount of? This. What's the charge of CN? They tell you that it's -1. So how many -1s do you need to bring +3 to -3? 6. 6. Formula, we've got it, right? It's Cr, Cn, 6, brackets, 3-. Parentheses inside, brackets outside. Did that first one make sense?
Yeah.
Maybe? Second one. This is what? Does this have a charge?
Yeah, your signature.
Coordination number is 6. What's the formula? If you want and you know what this is, you could abbreviate it.
Right, that's EN, right?
It's the end. So this would be +2. How many of these do you need?
6.
Each of these
3.
donates 2 pairs of electrons. You need 3 of them. So it would be nickel. I would write it as En for spacing. And then 2+. Yes.
What the charge of the inside?
The charge of the ion? No, only on the outside. Because everything in here cancels to become that charge. So you shouldn't put it on the inside. You notice I put it together here, but I put my final answer up there. All right, PTCl. PT with Cl. They tell you the overall charge is 2-. So how many, the platinum's got to stay 2+. There's going to be one of them. How many ligands of Cl-1 do I need in order to get to an overall of 2-? What do you think? Jake, 4.
4.
That's correct. Because +2 - 4 equals -2. That's the idea here. So then how would I format that answer? Coordination number 4 here. And this would be PTCl4. You're going to notice something a little bit strange here. I'm writing one atom in parentheses. And sometimes you'll see that. Sometimes you won't, sometimes you will. This is me indicating that we have a ligand by writing it in the parentheses instead of just writing PTCl4. But I have seen it as well where they don't write the double parentheses. I wouldn't stress it. And then what about this last one? Hey, is that one of those bidentates? Isn't that ox? But they wrote the charge there to help you out. How do I get, they're telling me I have 3 oxes for 1 iron. Iron is +3, and each of these is -2. So what would the overall charge of the whole thing be? -3. because 3 times -2 is -6, right? This is +3 for the metal. There's 3 of these, and each of them is -2. So 3 times -2 is -6. 3 minus 6 is -3. Overall charge. What's the coordination number here? Because this is bidentity. Bidentity. So it's 1 is 2. Look at how many marks this would work.
Oh.
That's hefty marks.
Where are the marks even coming from?
Yeah, there's like a threshold. There's 1, 2, 3, 4, 5, 6, 7, 8. So
6,
it's
7?
yeah. So it's one of those where if you reach like 8, they give you 6 marks. If you reach 6 or and it goes down like that. It goes down like that. All right, so last topic for the day. Yay, we are towards the end. Geometry, shapes and bond angles. So this is shapes and bond angles, A-level edition. Your friends, if you have any, in pre-ACE, are doing a test on shapes and bond angles today.
Oh, yeah?
Oh yeah, your brothers.
Yeah. Wait, what period do you have them?
He took it yesterday.
It's 4th period.
Oh, I think I didn't do it. That's not.
You can ask him how he did. I'm not able to share that info, but you can ask him how he did.
Did Brandon do it yesterday? You know Brandon?
Braden Garcia? Yes. You can ask him.
He didn't study.
Anyways, that's what pre-ACE is. Octahedral. You have to memorize the shapes, meaning that, if you recall, these were 90-degree angles. You may or may not remember. And this is a 90-degree right angle here. This is a 90-degree right angle here. And then these two groups from each other are 180. And you do have to remember that shape. These dashes means that going backwards, and this means coming at you. And so octahedral shape, you do need to memorize for your octahedral ligands. Tetrahedral, Cl minus. That's the tetrahedral shape, 1 wedge, 1 dash. Yes.
Does it have to be a metal to have ligands? Because it doesn't phosphorus.
There can be, I think it gets, I have this word chelation coming to mind, CHELATION. Chelation can happen with non-transition metals as well. It's whenever you have dative bonding going to your central element. But here we're specified looking at the transition metals. Linear, that's easy to draw, straight line, right? And this is square planar right here. In square planar, I'm going to show that one to you because I built it right before class. This is square planar. It looks like an X. If I flip it this way,
It's like a race.
it's got 2 that are coming at you, 2 groups coming at you, and 2 groups that are going backwards. We will be breaking out the model kits on Friday because we're going to need to see things 3-dimensionally better. So like the end of this lesson is the beginning of the next lesson. And so this is square planar, but look, it's a plane. It's 2-dimensional, like it flies flat on my hand. And you could alternatively write it like an X. Like literally, it looks like an X. When you write it like this, it's 2D X. But the traditional format is to write it like this, with 2 coming at you and 2 going backwards. That's called square planar, 4 groups square planar. And so draw the following with the correct dimensions. SF6. Here's what I would do. Knowing that it's octahedral, I would correct my answer. Line up, line down. 2 dashes back and 2 wedges to the front. And what would go around the sulfur on every side? Right. So this would be the correct 3-dimensional structure for SF6. What does that look like?
Oh,
This is SH6, but it has that same octahedral shape. This is what it would look like. 1 up, 1 down, 2 at you, 2 back. Octahedral. Good? So I would do line up, line down, 2 back, 2 front, always for octahedral. XEF4, which is our most famous square planar. How could you write it? XE in the middle. Hey, how many valence electrons does that have? Xenon? Isn't that a noble gas?
Yeah.
Remember, is that noble gas that actually had an electronegativity value? It's an exception. It can make bonds. Yes.
So, do we ever talk about this in like A level or not?
No, just it exists. It's there. It does that. That's the level. And so, what would actually happen here? This would be going back. This would be going to the front. This would be going back, and this would be going to the front. So it looks like this. F, 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 F. And they expect you to know that fluorine makes 1 bond because it has 7 valence electrons. They do not expect you to have to write them all, but they expect you to know that that's how the bonding works. All right, we're almost done. Woohoo, last slide. We did it. There are a lot of slides. Today's lesson. A lot of objectives. Okay, so some things here are coming soon. Like a lot of these words are like, okay, I guess that's a thing. It says when an excess of Cn minus ions is added to green iron, water ions, yellow
No, but it's
iron complex ions are formed.
you literally have like 4 hours.
Heated with dilute nitric acid and neutralize the product produces red crystals containing FeCN5 NO2 minus. NO is neutral and monodentate. And the actual question, what's the shape of this? What's the shape?
Oh, it says neutral.
Octahedral. Worth a mark. What's the oxidation state of iron in FeCN6 minus?
What do you mean and I died?
Minus 1 plus 6, negative 6.
I
That's X. So we're solving for X, right? Some of you did it in your head. Just be careful. If you didn't get the right answer was +2. So pat yourself on the back if you did get it in your head. If you didn't, you should solve it out. X is +2. You don't have to write the work. You can just write the answer. Do it in your head. And then deduce means you don't have to actually calculate. Like you don't have to show work. Deduce means, hey, you can figure that out, right? And then this one. What about this one? +3 is correct. Because the whole thing's -2. This is 0, right? So the NO doesn't count towards the charge. And then the Cn is -5. So it's X minus 5 equals -2 is the math that some of you did in your head. Bring 5 to the other side and X equals +3. And these were worth 1 mark. All right, so you have homework. You have homework and it's due on Friday so that you remember what you're doing. And then Friday we have our next lesson. So get started on transition metal. See you Friday for continuation. What? Oh.
We love drafting, man.
What time is it? 9:17?